In this video, we're going to look at Section 2 of Chapter 11, and we're going to be comparing two means. This is going to be a different setup than a matched pair setting that we looked at in the last chapter, in the last section of Chapter 11. And so our idea is this. We have a population, and again, we're doing some type of a measurement where we're measuring a quantitative measure of this. We're not looking at a characteristic, yes, no. We're actually taking a measurement. And there's a certain mean that this original population has, and there's a certain standard deviation that this population has. We would like this population to be normally distributed, but we don't necessarily need to have that. And then we have another independent population, and it has a mean, and it has a certain standard deviation associated with that. And again, we would like both these populations to be normal. And so we assume that we're taking two simple random samples from two distinct populations. So we'd be taking a simple random sample here of size N1 and a simple random sample here of size N2. These don't necessarily have to be the same sample size. They may, but they don't necessarily need to be. Very important in this setting is we have our samples are independent. This group is not affecting this group or vice versa. So theoretically, we'd like both populations to be normally distributed. And unfortunately for us, in most cases, we're not going to know this mean or this mean, and we're not going to know either standard deviation either. So we would sample from here, and we would get an X bar. And we would sample from here, and we would get an X bar. And we would also measure, take these sample of N1, and we could get the associated standard deviation from that group. And likewise, we can get the associated standard deviation from this group. So we know how those individual N2 samples vary within here to get this mean, and we know what the associated standard deviation is. And the question that we're looking at here when we're comparing two means is we want to know, are these two means equal? And so our statistics today, or our analysis today, is going to be looking at how can we determine whether these two means are statistically different or whether we have evidence that they're not different. So that's what we're doing. So we're looking at the sampling distribution of comparing these two X bars. So we'd take a sample, get an X bar, take a sample and get an X bar, and then we would look at the difference between these two. We would be subtracting them. And so that produces a new distribution, that if I take this mean and I subtract them, and if I do that again and take another sample from this population, I'll call that A1, I'll call this A2, and I take another sample from here, again they're independent, and I subtract them, we know that this difference and this difference are likely to be different. We want to know what would the standard deviation be for the differences between these in our new sampling distribution. And so let's look back at your sheet. So we're looking at the sampling distribution if we, again, take a sample from the first population, get an X bar, take the sample from the second population, get an X bar, and we're looking at how these X bars will vary. Now, the actual mean should be whatever this is, the difference between those two should be the mean for the difference between these two. So if we know what this mean is, and we know what this mean is, if we subtract these two numbers, that will tell us what our sampling distribution should center at. So kind of picture-wise, we're looking at this sampling distribution for the difference, and it should center at whatever the mean of the first population is minus the mean of the second population. And we know as we take samples from each of the two independent populations that when we subtract the X bar from each one, we aren't going to necessarily get right here at this difference. Sometimes a little higher, sometimes a little lower. And how do we describe that standard deviation? Well, I'd put the variance down first of all. The variance for the difference, remember from Chapter 7 when we dealt with random variables, is if you have two independent random variables, we don't add standard deviations or subtract standard deviations. If our random variable is looking at the difference between two random variables, we actually add their variances And this would be the variance of the sampling distribution for the first X-bar distribution. And this would be the standard deviation of the second distribution. And so we add the variances. So there's the standard deviation of the sampling distribution for the X bar 1. Here is the standard deviation of the X bar 2 distribution. And we need to add the variances. So this ends up looking like this. Now, unfortunately for us, we're not going to know these sigmas. These are going to most likely be unknown. Why would we know these if we don't know these? So here are our test statistics that we'll be working with when we are comparing two means. First thing we'll do is we'll look at if you are assuming that the two means, that the difference between these two means would be equal to a specific value. Now, quite often we're going to be testing to see whether these two are equal, meaning that this difference we're going to most of the time just assume that it's equal to 0. And so if we knew the population standard deviations of each of our two independent populations, we would actually be calculating a test statistic that would be a z-value. We would take what we got minus what we're assuming the difference to be, and then divided by the standard deviation of the sampling distribution for the differences between the two. Now, once again, we're not going to know those population standard deviations. Therefore, we have to calculate a t-statistic, just like we did in section 1. And we take what we got for the difference between the two minus what we're assuming the difference to be, which in most cases we're going to assume that this difference is 0, and then divided by the standard deviation of the sampling distribution for the difference between two random variables. And remember, when we have two random variables that we are subtracting, and also if we were adding, we take the variance of the first plus the variance of the second, and we add the variances together, and then we square root to find the standard deviation. So it looks a little ominous, but it will actually be pretty easy to work with as we go. Now, this little next section talks about how do we calculate this little degrees of freedom. And we'll come back to that as we look at an example. So let's just go to the example. We'll see it's not so bad. So we'll go and we'll do this hypothesis test, and we'll go back to the confidence interval question in a second. So I have this example again from the textbook. Not terribly interesting, but we'll deal with it. In a study of cereal leaf beetle damage on oats, researchers measured the number of beetle larvae per stem in small plots of oats after randomly applying one of two treatments, no pesticide or malathion, at a rate of 0.25 pounds per acre. The data seems to be roughly normal, and so they're looking at measuring how much beetle damage there is to a specific plot of oats. Okay, so not real important. Let's just look at our numbers. So we basically have two groups. We have two different treatments, and look at our sample size. Their sample sizes are not real huge, but we are told that the data appears to be approximately normally distributed. So they would have measured how much beetle damage is done if the control, no pesticides were added to these 13 plant areas that they're looking at, and they'd count how much beetle damage is done to each of these different patches. And they had 13 patches that they're looking at here. The mean of those 13 numbers was 3.47 with a standard deviation of 1.2. Now that is a sample standard deviation and a sample mean. Now notice they also applied the pesticide to the other plants, used 14 plots this time, and we can see that it looks like the mean of all 14, counting how much beetle damage was done on the leaves, that you have looks like it's a lesser amount on this one, and notice that the standard deviation of the individuals is significantly smaller. So how do we do a test? Is there significant evidence at a 1% level that the malathion reduces the mean number of larvae per stem? So here are our little checks. First of all, we do want simple random samples. We would like both populations to be normal, and they need to be independent. If they're not independent, we cannot perform this test on this data. So we're going to start out, and we're going to assume that the number of larvae for the control group and the malathion group are going to be exactly the same. In other words, their means should be equal, which means that the difference between these two should equal 0. Alternately, the control group we think will have more larvae bites on it than the malathion group. So the mean here should be higher than that mean, meaning that the difference between these two will be something positive. Okay, and so here's my picture. And so each time we do a hypothesis test, remember we're kind of doing the same thing. We set up our hypotheses, and we're going to assume the mean is a certain value. We're assuming the difference is 0. I like to draw a picture and plot what I'm assuming right down in the center. Now what do? Now we take our sample. And our sample is we had the control group and the malathion group having these two values for the amount of damage done on the average. So we're getting a difference of 2.11. Plop it in your picture. Now I haven't measured what the variability is for the sampling distribution yet, so I don't know if I'm very accurately placing this 2.11 down. Maybe it should be down lower, maybe it should be up higher. We'll see as we go through and calculate the test statistic. Okay, so now I'm ready to do my test. So always start out, first step, get your hypotheses, draw a little picture, plop what you're assuming to be the mean right down in the center. Now I get my sample. Plop down where that sample is. If this had been a two-tailed test, then we would again symmetrically color the other side. So very similar to what we've done in the past. And now I'm ready to calculate my test statistic. Our test statistic is the difference between two means. And we want to know how likely is it in our picture to get the difference between these two means being 2.11 or higher. I don't know the population standard deviations, therefore I need to calculate a test statistic that is a t-value. I take what I got minus what I'm assuming divided by the standard deviation of the sampling distribution, which is take the individual standard deviation squared plus the individual standard deviation squared and square rooted. So we have the standard deviation of individual squared over 13 and the standard deviation for the malathion squared over 14. Carefully calculate this out, and I get a test statistic that is 5.8. Now, how did I know what to use for degrees of freedom? Well, let's turn back the page and we'll look at that. There are different ways. We're going to use the least complicated way. One way is to use this bear of a formula. We're not going to use that way. We're going to use, so calculating the degrees of freedom can be cumbersome. We are also permitted to use an approximate value, and that is if we take the two sample sizes we had one was 13, one was 14, subtract 1 away from the sample size like we do on a one sample type test, and you take the lesser of the two. So we have one of our sample sizes was 13, so it would have 12 degrees of freedom. One of our sample sizes was 14, and that would have 13 degrees of freedom. We would take the lesser of the two and take the 12. Now, there's also something that we'll see that when we do some analysis is sometimes they'll talk about pooling. And pooling is something that we will not be doing. But the pooling idea is where you're assuming that the two variabilities or the standard deviations are equal. And if you're assuming that there would have the same amount of variability from each of your two independent populations, then actually there's a way to calculate the number of degrees of freedom just by adding the two sample sizes less 2. But then you have to come up with something called the pooled standard deviation. And again, this method for number 3 is something you're not held responsible, but you may see it if you look up or listen to some type of a video. You may hear something about pooled standard deviations. Okay, so let's turn back. So we need to finish. We know that we have a t test statistic, and we have 12 degrees of freedom, and I can use my t CDF going 5.8, comma, large number, and then comma, put the 12 degrees of freedom in, and I find my p-value. So very, very similar in the analysis. And then I have to make my decision. Now, I said nothing about a significance level. Oh, I did so. I said 1% level. Regardless of level, that is small. So, at a 1% significance level, yes, there is evidence that the malathion does reduce the mean number of larvae per stem. So, our setup is very similar in all our hypothesis tests. Set up your hypothesis, draw a little picture centered where you're assuming the mean to be. Look at your statistics of what your sample gave you. Plop it on your picture. If it's one-tailed, you're going to shade one direction. If it's two-tailed, you'll not just shade the one tail, you'll shade the other tail. Calculate your test statistic. Find your p-value. Make your decision. Now, the last thing we're going to look at here is calculating a confidence interval. And I guess we just need to move to the top of this page. Sorry for the shuffle. Confidence intervals always set up the same way. We're going to be studying confidence intervals the rest of the time. And you'll always take the estimate you got from your sample plus or minus either a z or a t-value, and then times the standard error. They're always calculated the same way, okay? Regardless of whether we're in Chapter 10, Chapter 11, Chapter 12, Chapter 13, Chapter 14. And so if I'm trying to find a confidence interval for the difference between two means, I'm trying to find an interval estimate for what mu minus mu is. So I have here, we really want to know what this difference is. Now, once again, we're not going to know this number nor this number. We're hoping that this x bar 1 is very close to mu 1, and we're hoping that x bar 2 is close to mu 2. However, we're not silly enough to think that when we sample, we're going to get exactly these numbers. So this is our interval estimate for the difference between these. And so we take what we got, plus or minus, and this would be a t-value if we don't know the population individual standard deviation. And then it's times the standard error, and that's the variance of our first population sampling distribution, and there's our second sampling distribution's variance. And we add the variances and square root to get the standard deviation of the sampling distribution for the differences between the two. Now, let's look at a confidence interval on the next page, and then we'll look back at this little setup I have here. So I have a situation here in which we have males and females and dealing with, and you can read the question, but it's dealing with how much earnings there were in the summer between males and females at a particular college. And so we know that the distribution will be strongly skewed to the right because you're going to have a minimum of zero income that you can make, and then you could have people who could make very, very large amounts of money. But notice the sample size here. So our distribution, even though we would have skewing in the individual data distributions, we would end up, because of the central limit theorem, being able to look at the sampling distributions as being approximately normal. Okay, so let's get to this confidence interval. So I want to find a confidence interval for the difference between the summer earnings for males and females. So there is an actual mean for males, and there is an actual mean for females. I don't know them. So I take an x bar from here, and I take an x bar from here. And if I subtract those numbers, again, I'm not silly enough to think that these two numbers are exactly the same as these. So we want the interval estimate for that difference. So there's the males minus the females. X bar, X bar. And I could switch it and put it the other way, but I'm just going to choose to have the difference be the males minus the females. Plus or minus, now I would need to find my t-value for a 90% confidence interval. And I would look up and I'll find that my degrees of freedom, once again, is I would look at these two, take the smaller sample size, less 1, and that would be the degrees of freedom. Now, I don't have this number in the table in the back of my book. This basically, once we get these large sample sizes, you're pretty close to this being a z-value. Z-value here I think is 1.6 0.645. So ultimately, as the sample size gets larger and larger, this turns closer and closer to a z-value. But this would be approximately the number I would use. And then I set up my values here. My standard deviation of the first population squared divided by the sample size, standard deviation squared divided by the sample size. That would be the variance for the difference. Square root it, and I've got my standard deviation. And I calculate my interval. And then you can read, that would be my interpretation. Remember that 90% of the calculated intervals will contain the actual population difference between the two populations. So I'm quite likely to have the difference in there somewhere. Now, the very last thing I want to look at is just a little shortened version of if you're calculating a hypothesis test. Usually, when we are making our hypothesis test for the difference between two independent means, usually we're assuming that they're equal. You can have this difference be something different from 0. But on all the ones that I give you, you will be assuming that the difference between these is 0, which means you're going to be assuming that the two populations have equal means. And then your test statistic, remember on the other page, it was what you got minus what you're assuming. Well, now you're going to be assuming 0 in this setting. And so that's just why I gave that one specific test statistic. That the other is a generalization, so regardless of what you're assuming the difference to be, that would always work. So for us, most of the time, this will be the shortened version of the formula, because most of the time we'll be assuming that these two populations that we're looking at are equal, and then trying to find out whether we have information from our statistics to say that it's higher than, the difference is higher than 0, or possibly less than 0, or just not equal to 0. So that's kind of it in a nutshell. Now you're ready to practice.